Great. So hello, everybody. Thanks for having me in this session. Today, I'll try to give a short overview of work in additive manufacturing with two different directions, as you can see from the initial slide. And so this is joint work together with my colleagues from my group, Martin Geier, Konstantin Kutscher, and also with a group of Laura de Laurentiis. And here, especially the powder scale simulations have been subject of the PhD thesis by C.V. Jose with some support of Hezamedin Zafari. So as maybe some of you are not too much into kinetic schemes and especially Lattice Boltzmann methods, I would just give a nutshell idea about how these models can be understood from a principal point of view. And then I will report on some ongoing work to model Shotcreep Printing. And then the second part also describe some activities and give some preliminary results on thermal scale simulation, powder scale simulation of selective laser melting. So Lattice Boltzmann methods have been introduced some decades ago, maybe 3 decades ago. And in the continuous drive for finding better models and simulation approaches for transport problems, which of course are still difficult to this day. And the key idea here is that you resort to some sort of mesoscopic physics where you don't think in terms of the hydrodynamic variables, but in terms of what we call distribution function. And this distribution function describes probability states to find a microscopic system in certain states. The key is now that this basic equation, the Boltzmann equation, was of course developed a long time ago by Ludwig Boltzmann. And it's well known that this describes all macroscopic transport phenomena to great accuracy. But the key is that this Boltzmann equation has to be drastically simplified to be useful for fluid dynamics on a macroscopic scale. And so what we use is sort of a simplification of the original Boltzmann equation, which then results in a first order PDE, the so-called Lattice Boltzmann equation, which simplifies the physics in the sense that the distributions travel similarly to what you could imagine as particles on a grid of a certain symmetry. And the key is once you know this distribution function, you can compute the so-called hydrodynamic moments, which are density, velocity, pressure, stress, and so on. So it's sort of an implicit approach to transport simulation. That is, you solve a simplified Boltzmann equation. And of course, the key is that an accurate and also efficient approach. In the end, you also end up with a grid-based simulations with all the pros and cons, local refinement, and so on. And now you can modify this collision operator to include more complex physics. So starting from simple Newtonian fluids, you could then add contributions to the collision operator, which would result in modeling multi-phase flow or multi-component flow, compressible flow, and so on. So, but the key approach is always this sort of simplified finite difference scheme that tries to solve a simplified Boltzmann equation. Now, why should this be a good idea? Well, it has been shown that for many different types of flows, these kinetic methods, and especially these Boltzmann methods, can be demonstrated to work pretty efficiently. I will not go through all the details here, but typically, as we have the nonlinear parts of the model as local terms and the advection terms are being solved exactly by construction, you have an explicit scheme which runs very well on accelerator hardware such as GPUs and other ones, so like FPGAs and so on. And as they're explicit schemes, you can also couple them relatively easy to other schemes. For example, when you couple to radiation, but even though radiation can also be modeled by Boltzmann models. And it has also been shown that this is a very efficient approach for CFD, for turbulent flow. So there are some hints that it may make sense to use kinetic methods for the transport problems you find in additive manufacturing. And the first class of problems I'll describe here shortly is so-called Shotcreep printing. So what you see here, I didn't add a movie because that would not help too much and would probably be highly distorted here. So you have a highly turbulent jet, and this jet contains cement paste, it contains particles, but also air. And once you have a decent mixture and decent process conditions, you can then sort of print forms then made of concrete. And of course, you can add stabilization and things like this. But the key is to understand now the physics of this jet. And of course, obviously, this is not a simple problem because you have multiple challenges here. You have multiple phases. So you have air and cement paste and grains. You have multiple components because not only the concrete or cement, but you also have additives to accelerate hardening and other features. So then the flow is turbulent. You have a high density ratio between the air and the cement paste. The cement paste itself has non-Newtonian rheology. And if you want to do it right, you also have to take into account that the air is being compressed during this process. So you don't get away with a perfectly incompressible solver. And of course, as you have these droplets and spreadings, you have a multi-scale problem that spans at least 6 orders of magnitude. So it's not a simple problem. And what we're trying to do is to come up with a suitable model for this jet. And so I'll just report on the first steps because this is ongoing work. So first you have to tackle this feature of non-Newtonian rheology. So you can start with Bingham model, go to more complex Herschel-Balkley model. Could also consider to implement the Russell model, but we believe presently that the time dependency in the Russell model might not be too relevant because we're looking at the jet and this is a short time scale. And so we don't think that this droplet dynamics will be very much depend on the time dependence in the rheology. So we try to stick with the Herschel-Balkley model. And so in order to implement this, you, as I said, have to modify the collision operator. That's somewhat complicated, but I'll just show you the result. Now you look at the channel flow and compare to an analytic solution for different exponents here. And what you see is that we are able to reproduce the different velocity profiles for different exponents pretty well. And so then, of course, you also have to consider implementation issues because this is a nonlinear problem where the shear stress depends on the local velocity and vice versa, including the boundary conditions. So we have been thinking about this, and the next level was now then to describe a nonlinear flow. And here you see a Taylor-Couette flow, which partially consists of a plug flow. So let me just try to show this here. So you have an inner cylinder that's rotating, or an outer one, depending on your frame of reference. And it's well known that you have a plug flow because you have shear thinning flow. So here in the outer part, shear stress is lower, and then you start getting a plug flow. So that's a non-trivial phenomenon. It's not comparable to the simple Newtonian Couette flow. And we are able to reproduce the profiles for different rotation rates with second order accuracy. And so that's nice because then now we are starting to become closer to describe the slow flow regime. So you have cement paste, which then just spreads, which is nice, but of course far from the regime that we are interested in. And so the next step is then to add some features so that we can also tackle high Reynolds number flow, because the the final stage jet is of course highly turbulent. And so we found that the multi-phase model generates pressure fluctuations. So we introduced some filtering. I won't go into details now, but what is essentially being done is some sort of limiter for high frequency oscillations. And once you add this, then you can see something where we can have here the first impressions. Now, does this work? Yeah. So you see the jet entering and then immediately losing stability and creating these droplets which interact with the air phase, introducing the turbulent decay. And so this is just what we had last week. So this is really work in progress. And of course, it's still far away from all the features that we want to see in the multi-phase, multi-component jet. But it's a first start. The density ratio here is already correct, but the air is not really compressible yet. So we're working on extending this type of model class and hope to report on this on a later occasion. So the next part is, as I said, essentially work done in the group of Laura De Laurentiis, who is also here. Hi, Laura. So here we have a different topic. It's still additive manufacturing, but it's on a different scale, powder scale simulation of selective laser melting. And we heard about this today also in the last talk. So maybe we'll get back to some issues here. And of course, as you all know, we have then often problems depending on the process parameters to obtain homogeneous results, reproducible results. And you find different problems of discontinuous path properties or balling phenomena. And so, of course, you have to understand this process in as much detail as you can. And simulation and modeling is our way to approach this. So here, again, we start on a small scale. In the end, we will want to look at a small scale where we include all essential phenomena, as is listed here on the left-hand side. This is part of a large-scale project that I don't have the time to describe in more detail. But so essentially what is done here, you position the particles, and here the lights DEM solver is used. And then you use the Lattice Boltzmann code for all the transport aspects that I will describe in the next slide. So essentially you have a phase field equation for the multi-phase flow. And then you have to, of course, solve the momentum equations coupled with the pressure equation. That's all somehow married in the Lattice Boltzmann framework, so I won't go into details. And then, of course, you have a temperature field, and a temperature field also influences the transport parameters. So you have a coupling of different fields: the phase field, density field, velocity field. Phase field couples with a temperature field, and the temperature field also of course modifies the momentum equations, and the omega here is indicating the transport properties, both for heat transport but also for surface tension, and of course all these equations are being solved simultaneously. And then of course you have lots of parameters to be studied. And here in the next few slides, I will show some preliminary results that we had. So we induce some thermal load, mimicking some laser. And of course, the scale of the simulation is still very small. So it's about 1 millimeter, so a sub portion of a cubic millimeter, with some more or less suitable boundary conditions. And so Sylvie Rosé has done some sensitivity studies looking at the different contributions from gravity, from surface tension, and for example, here a qualitative view introducing a temperature-dependent surface tension definitely plays a role when you look at the shape and the qualitative shape of the humps and peaks that are being created during the laser impact. And so lots of these studies have been done and are presently being done. So essentially, I would now, because time is essentially limited, just show you some decent results on small scales for flat surfaces. So we have done initial studies for temperature distribution as a function of grid resolution. And as you can see here from the phase field representation, this also gives slightly different results. So what I can show you here are not yet grid independent results. But the key parameters here that we analyzed in the validation study are the molten region width and depth. And this is then compared to NIST experimental data for 3 different sets of parameters as listed below. They are not substantially different, but more or less similar. But of course, still the resulting data for molten region geometric properties are differing. And so what you can see here, first the length of the melt pool, you see the simulation is blue as compared to the experimental data from NIST. And you see a decent difference. So qualitatively, this looks reasonable, but quantitative view, there is still some 50% deviation partially. So you can't really say that we are there yet. If you go to the width, then things look slightly better. So deviations for at least case A are very small, but when you look at other properties like the depth of the molten region, again, you see substantial deviations. And so it's fair to say that we fundamentally have included probably the correct partial models, but still there are numerical issues. For example, in this small spatial region of the strongest interaction of the beam with the solid and the fluid, we don't have much resolution yet. So we're working on mesh refinement issues. And I guess, especially the talk before this one here was very helpful in looking at refining the model and looking if we can also reproduce these types of oscillations. That would be, I guess, a great next step. So coming to a conclusion, I just want to show you in a few minutes that kinetic methods, especially the advanced LBM methods that we use for both the Shotcreep Printing modeling as well as for the powder scale simulations, are a suitable model class, especially as they are massively parallelizable, and that might help in decreasing wall clock time of these complex simulations. Still, we have very challenging multi-field, multi-scale, multi-X problems, and there's still quite a bit to do, but maybe I can report on this at another occasion. Thanks very much.
Yeah, thanks a lot for this very exciting overview. There are already some questions here. Daniel, please.
Yeah, excuse me. Maybe I've got it wrong, but could you comment? I mean, I understand those are different projects and different problems you handle, but I'm a little bit surprised that you, in the Shotcreep case, you basically model only the gas flow. No. So the flow of, I mean, what happens in the gas phase. So you do not seem to model what how the concrete is sticking on the substrate.
No, we model the concrete and the air as different phases, but in the example I showed to you, it was a periodic space. It was not a confined space with a wall where the concrete sticks. That's not yet the case. We are just now focusing on the stability and accuracy on the breaking up of the jet.
All right. So this was meant to come later.
Yes.
Okay, I understood. And in the powder bed fusion case, you didn't seem to model movement in terms of gas transition. It didn't look like you had a keyhole model implemented.
So what we model is the laser beam that induces a thermal load, which leads to a melting of the solid, and the molten flow is then solved or described by sort of Navier-Stokes type solver. What we don't have yet is the transition from the fluid phase to the gas phase.
Okay.
Yeah, so there are some parts missing. I would perfectly agree to you. Okay. And this is why we are now getting closer and closer. We see the discrepancies to the measurements, and but we also have to face numerical issues still. So we'll first try to get consistent results with the preliminary models we have, and then we would add new model properties.
Understood. Thank you very much.
Thank you.
Okay, then we have a question by Ernst here.
Manfred, thanks a lot. Very interesting. I think what is in particular interesting with, well, Lattice, Boltzmann and additive manufacturing, you are limited by the process to small time steps anyhow. If you want to follow, like in the Shotcreep or in the SLM process, if you want to follow the source in a sense. And in Lattice Boltzmann, as you are computing explicit time steps, each time step is cheap. So this fits, I think, very well together, these two things. On the other hand, as you mentioned, that you have a time scale range about 8 orders of magnitude. Is there any possibility to make a kind of homogenization like that, what Michele Chiumenti showed, in a sense that you, well, would not follow the Shotcreep itself, but look at one layer immediately so that you can put together a sequence of time steps?
Yes, of course, you can do that. I mean, as with any short scale method, you can create a variant that, for example, would not try to resolve all the particles, all the droplets, and then create some larger scale model that has some homogenized properties. And then, of course, immediately you would see that the corresponding time scale would be drastically increased. And then you would probably be able to also do some sort of real-time modeling. But in order to create such a reduced model, we would always try to understand the process before. So now we're in this tedious part of trying to resolve all the physics, at least to a certain extent, and then learn from this and then create a reduced model that is, of course, much more capable of describing real-world production scenarios.
Okay, thank you.
All right, Ferdinando.
Yes, Manfred, thank you very much for the presentation. I have a simple but fundamental question. So you start from complex PDEs and then you solve these PDEs using Lattice Boltzmann approach. So how do you do, I'm sorry for the noise, how do you do this step? So you mentioned briefly how you go from the generic equations, the PDEs to the Lattice Boltzmann scheme, but can you give us some details on this aspect?
Yes, I can try to describe this qualitatively. So let's imagine you want to solve a transport problem. When you look at the fundamental Boltzmann equation, without talking about any simplification or numerical aspects, then you can show that by looking at the moments that you can compute from the Boltzmann equation, that these correspond to hydrodynamic quantities. Just as I said, like density and momentum pressure fields, stress fields, and so on. So there's an infinite order that you can identify on different time scales. Like, for example, if you do a multi-scale expansion with the original Boltzmann equation, the PDE, then you can show that on the first order time scale, there you get as a result continuity equation. On the second level, you get the Euler equation. On third level, you get the Navier-Stokes equation. On the next level, you get Burnett equation, and so on. And so this is the fundamental feature. You look at different time scales that are being modeled by different contributions of the fundamental probability distribution function. So you start with the equilibrium function, you have then the next level, non-equilibrium contributions, and so on. Now, that's the background scenario that is known for 100 years. Now, if you look at a more complex fluid behavior, for example, a two-phase flow, you add specific components to the collision operator, and then again do this multi-scale analysis, and then find out to which respect you now meet the target macroscopic equations, and you modify the collision operator as long as you have this. But this is only done once, of course, in the development of the model. So essentially, the key is you either start from the mesoscopic scale itself, because you know it's fundamental, but typically this is often too expensive. But if you start coming from a macroscopic point of view, you have your target equations, and then you modify essentially the collision operator in the Boltzmann equation to get the same macroscopic behavior by using your modified Boltzmann equation. That's the key. But that's what is done once, so the theory, so to speak. And once you know how to construct the collision operator, you can then implement it and do the work.
Okay, thank you. Thanks.
All right. So I don't see further questions, also not in the Q&A. Yes, okay, there's one. So Alexander is saying, thank you for the interesting presentation. What was the demanding computational time for all the couplings? Thanks. So the question is for the computational costs, essentially.
So that depends now very much on the specific model that we're looking at. Presently, the Shotcreep simulations, they are not yet expensive because the resolution is limited. But if we would go to the desired final resolution, where we are talking about like 1 billion grid cells, 1,000 cubed, to resolve the droplets and the particles. And then we're talking about big high performance computing clusters that are being utilized for days. We could reduce this to at least an order of magnitude less by using GPUs, but then we would have to port also, for example, the particle code where we want to model the advection of particles, and that's not so easy parallelizable. So presently, I think when you go to the production scale of the Shotcreep, this will have compute times of days on a large machine. And on the long run, when we would be able to port this to GPUs, multiple GPUs, we would talk about desktop size machines on the order of a few days. For the powder scale simulation, that depends very much if we will manage to have this local mesh refinement available. Right now, this is work in progress. And of course, once you have a uniform grid, then you will be punished because the extreme dynamics at the point of interaction with the laser beam with a melt pool, you want to resolve this. But if you resolve this adequately, then you spend too much degrees of freedom. So here we are still, I think, not very competitive yet. But again, this work in progress, our latest Boltzmann code, which is the platform that is being used here, has of course local grid refinement, but that has to be done adaptively, and that will take some more time. So it's work in progress.